Namaste, my friend, and welcome back to NEET Physics with Typical Monk. This is Class 2, and today we set the world in motion. Last time, we learned the grammar of measurement, units, dimensions, and errors. Today, that grammar begins to speak because we describe how things move along a straight line. Sit with one gentle truth first. Motion is nothing more than position changing with time. Everything else, velocity, acceleration, the three equations you will come to love, is just a careful way of watching that change. When Arjun first met kinematics, he tried to memorize formulas blindly, and they slipped away. The day he learned to see motion as a graph, to read slope and area, the whole chapter became one clear picture. Today, we build that picture together. Take a slow breath. Let us begin. So what will you carry home from today's class? First, distance and displacement, and why one carries a sign and the other never can. Second, average and instantaneous velocity and acceleration, the four quantities that describe every motion. Third, the three equations of motion, and how a falling body obeys them under gravity. Fourth, reading position time and velocity time graphs, how slope gives one quantity and area gives another. And fifth, the NEET drills, assertion and reason, match the column, and a full worked numerical, so that everything you learn today, you can also score with. Ready? One idea at a time. Let us start with the raw material of motion. Distance is the whole length of the path traveled. It only ever grows and it carries no direction. Displacement is different. It is the straight, shortest gap from start to finish, and it carries a sign that tells you which way. Walk 5 meters forward and 5 meters back, and your distance is 10 meters, but your displacement is 0. Now average velocity. It is displacement divided by the time taken. Because it is built from displacement, it is a vector. It points somewhere. Average speed, by contrast, is distance over time, and it never points anywhere. Then comes instantaneous velocity, the velocity at a single instant, found by shrinking the time interval until it very nearly vanishes. On a graph, it is simply the slope at that one point. And acceleration is the rate at which velocity changes. Change in velocity divided by change in time, measured in meters per second squared. When Ria feels a car push her back into the seat, that push is acceleration made real. Now look at these two graphs carefully, because a physicist reads motion far more than she calculates it. On the upper graph, position against time, the slope at any point is the velocity there. A steep slope means fast, a gentle slope means slow. And ninth, breathe the slope, and you've read the speed. Notice this position time curve bends upward, and a curving line means the slope is changing, so the velocity is changing. A curved position time graph is the signature of acceleration. Now, the lower graph, velocity against time. Here, the slope is the acceleration, how quickly the velocity climbs. A straight sloping line means constant acceleration. And here is the quiet gift of the velocity time graph. The area beneath it equals the displacement. So one graph gives you two things. Its slope gives acceleration, and its area gives displacement. Priya solved half her kinematics paper just by reading these two shapes. Now let us meet the three equations that solve almost every straight line problem. They hold under one condition: the acceleration must be constant. First, these use four letters: U for initial velocity, B for final velocity, A for acceleration, and T for time, with S for displacement. The first equation says V equals U plus AT. It links velocity to time. The second equation says equals ut plus 1/2 a t squared. It links displacement to time. This is the one you reach for when you want how far in a given time. The third equation says v squared equals u squared plus 2s. It links velocity to displacement. And notice it carries no time at all. Use it when time is neither given nor wanted. And one more that NEET loves, the distance covered in the nth second, which is u plus over 2 times the quantity 2n minus 1. Keep these four together, and straight line motion holds no surprises. Time to solve a full NEET numerical together, slowly, the monk's way. A ball is dropped from rest at the top of a building 45 meters tall. Taking g as 10 meters per second squared, we want the time it takes to reach the ground and its speed as it lands. Step 1. Write down what is given. The initial velocity u is 0 because it is dropped from rest. The acceleration is g, 10 meters per second squared, and the height h is 45 meters. Never skip writing the given data. Step 2. Choose the formulae. For the time, use h equals u t plus 1/2 gt squared. Then, for the speed, use v equals u plus gt. Pick the equation that fits what you know. Step 3. Substitute for the time. 45 equals 0 plus 1/2 times 10 times t squared. So t squared equals 9, which gives t equals 3 seconds. Step 4. Now, the speed. V equals 0 plus 10 times 3, which is 30 meters per second. Step 5. The answer. The ball takes 3 seconds to fall and lands at 30 meters per second. Given, formula, substitute, speed, answer. The same 5 steps solve every free fall problem NEET can ask. Let us make these equations permanent, because NEET tests them again and again. First, hold this in your mind. All 3 equations assume the acceleration is constant throughout the motion. If the acceleration changes partway, these equations simply do not apply. Second, for a body in free fall, you replace it with g and choose one direction as positive. If down is positive, g is positive. If up is positive, g is negative. Fix it once and keep it. Third, the art is to pick the equation that skips the unknown you do not care about. If time is not asked for, avoid the equations that contain time. And that is exactly why the third equation shines. V squared equals u squared plus 2as carries no time, so when time is neither given nor wanted, it is the fastest road to the answer. Rohan saved minutes in every paper the day he learned to choose the equation instead of forcing one. Now sit up straight. These 5 lines are what NEET actually asks year after year. 1. Know the 3 equations of motion cold and know exactly when each one applies. Constant acceleration only. 2. The slope of a position time graph is velocity, and the area under a velocity time graph is displacement. Now, a single idea unlocks most graph questions. 3. The distance in the nth second is u plus a over 2 times 2n minus 1. This is a favorite trap, so learn it as a separate formula, not by guessing. 4. In free fall, fix a sign convention at the start and keep it for the whole problem. Most sign errors come from switching midway. 5. For relative velocity in one dimension, subtract the velocities when the bodies move in the same direction and add them when they move in opposite directions. Let us drill the NEET way. Remember the 4 options. Option A, both statements true and the reason explains the assertion. Option B, both true, but the reason does not explain the assertion. Option C, assertion true, reason false. Option D, assertion false, reason true. First one, assertion, the slope of a position time graph gives the velocity. Reason, velocity is the rate of change of position with time. Think like Arjun, check each statement alone, then check the link. Is the assertion true? Yes. Is the reason true? Yes. And does the reason explain the assertion? Perfectly. Slope is rise over run, which is exactly change in position over change in time. Both true. Reason explains. Option A. Second one, assertion, displacement can be 0 even when the distance traveled is large. Reason, displacement depends only on the start and end points. Both are true, and here the reason is the very cause. Walk along you back to where you began and the endpoints coincide, so displacement vanishes while distance does not. Both true. Reason explains. Option A. Third one, assertion, a body thrown straight up has 0 acceleration at its highest point. Reason, its velocity is 0 at the highest point. Check the reason first. True. The velocity really does vanish for an instant at the top, but that is exactly the trap. The velocity is 0, yet gravity never switches off, so the acceleration is still g downward. The assertion is false, the reason is true. Option D. A quick match now. Say each answer aloud before I reveal it. The slope of a position time graph, velocity. Rise over run is change in position over change in time. The slope of a velocity time graph, acceleration. How steeply the velocity climbs. The area under a velocity time graph, displacement. Velocity multiplied by time, sum the cost of motion. And the area under an acceleration time graph, the change in velocity. If all four came to you before the revision, the graph picture is becoming yours. Here's a favorite new NEET format. I will read some statements. You silently count how many are correct. Statement 1. The area under a velocity time graph gives the displacement. Hold your verdict. Statement 2. The distance traveled can be less than the magnitude of the displacement. Think carefully before you answer. Statement 3. The three equations of motion require a constant acceleration. So, how many are correct? Two statements, the first and the third. The area under a velocity time graph truly is displacement, and the three equations truly do need constant acceleration. But the second one falls. Distance is the whole path, so it can never be smaller than the straight displacement. It can only be equal or greater. That single reversal is the trap NEET sets, and now you will not fall into it. Now let me save you some marks. Two myths that trap thousands of students every year. Myth 1. At the highest point of a throw, the acceleration is zero because the velocity is zero. It feels so natural. Nothing is moving, so nothing is accelerating, no? Arjun believed this for months. But here is the truth. The velocity is zero at the top, but the acceleration is still g pointing downward the entire time. Gravity never pauses, not even for that one still instant. Myth 2. The three equations of motion work for any kind of motion. If they solved the last problem, surely they solved them all? The truth, they hold only when the acceleration is constant. The moment the acceleration changes with time, these equations break, and you must use graphs or calculus instead. A powerful tool, yes, but only within its one condition. Time to test yourself, rapid fire. Here is the rule. I ask, you answer in your head before the reveal. No pen, no paper, just the equations you built today. Question 1. A body starts from rest with an acceleration of 2 meters per second squared. What is its velocity after 5 seconds? V equals u plus at, so 0 plus 2 times 5, 10 meters per second. Question 2. What does the slope of a velocity time graph give you? Acceleration. Question 3. Starting from rest with acceleration 10 meters per second squared, what distance is covered in 2 seconds? 1/2 times 10 times 2 squared, 20 meters. Question 4. Two trains move in the same direction at 20 and 30 meters per second. What is their relative speed? Subtract for the same direction, 10 meters per second. And question 5. A ball is dropped from rest, g is 10 meters per second squared. What is its speed after 4 seconds? 10 times 4, 40 meters per second. If those came quickly, you have truly understood today's class. Let us gather the whole class in one slow breath. Distance is the total path traveled, while displacement is the signed straight gap between start and end. Velocity is the rate of change of position, and acceleration is the rate of change of velocity. The three equations of motion hold whenever the acceleration is constant. The slope of a position time graph is velocity, and the area under a velocity time graph is displacement. In free fall, fix one sign convention at the start and keep it for the whole problem. And next class, we lift motion off the line and into a plane. Motion in a plane and vectors, projectiles, uniform circular motion, and how vectors add. Do not miss it. And so, my friend, we have set the world in motion. It may have looked like just a few equations and 2 graphs, but understand this. This is how every moving thing in physics will be described. Every projectile you will ever launch, every planet, every electron drifting through a wire, each one has a position that changes, a velocity, and acceleration. Arya, Arjun, Priya, and Rohan all began exactly where you are right now with this one class. Be patient with yourself. Tonight, draw one velocity time graph and read its slope and its area. Slowly, once. One idea at a time, you'll crack NEET. Of this I am certain. If this class brought you clarity, subscribe to the channel so the next one finds you. Until then, keep going. I will see you in the plane.